last thing we're going to look at this week is how we can start to use some of what we've learned about matrix algebra to apply it to what we know about stats. So the first thing we're going to do is start talking about a data set as a matrix. So we can think of a matrix X as a matrix n by p, where n is the number of observations and p is the number of variables. And so we're going to think about how we can use matrix methods to get some of the descriptive stats that we've learned about in the past. So the first thing we want to do is get the mean of each variable. Normally we would maybe take the mean of each column separately. There are functions, of course, in R that can give us all the means simultaneously, but how do we do this with matrix methods? So the first step is we're going to take a vector of ones of size n, and we're going to call this L. And then if we transpose X and multiply by L, divide everything by n, that's going to give us what's called a mean vector, or X bar. And this is a vector of the means of each variable or column. So formally, X bar is 1 over n, X transpose L. And so let's look at an example of how this works. So what is the mean vector of this matrix? First of all, this matrix is 4 by 3. So how do we get the mean vector of these 3 columns? So we're going to transpose our matrix. We're going to multiply it by 1 over the number of observations. And we're then going to multiply everything by this vector of ones, that is this vector of 4 ones. So we're dividing everything by 4, which is the number, again, the number of observations. And then multiplying it out by this vector, you see that we have our transposed matrix is 3 by 4 times 4 by 1. That's going to give us a 3 by 1, which winds up being the mean vector. So we can check this in R, of course, using matrix methods. So I'm going to create my original matrix. I'm going to create my vector of ones. Then I am going to multiply my 1 over 4. So here, instead of 4, I'm using the n row functions. That just tells me how many rows there are in X, or the number of observations. So that's just something we can always do. Instead of counting, we can just use the n row function. So 1 over n row times the transposition of X times my vector of ones. We see that gives us our mean vector here. And of course, the easy way in R is just to use the call means function, and we see we get the same result. So here's a practice example, and we'll use this Y matrix for a bunch of practice examples here. So just, you can, if you are up for practicing this, you can go ahead and try to get the Y bar, the mean vector of Y. So again, Y here is a 3 by 2, so we'll get 2 means. The answer is on the next page, so pause it here if you want to try to get it. And I will show you what the answer looks like in R. I'm not writing it out. So here we get the answer in R for confirmation. We see that it's 4 and 5. So now that we have a mean vector, we can use that to center our original data, which is something we often do. So just as a refresher, what conditions are needed to be met to subtract 2 matrices? We want to know this because to center our data, we need to subtract each observations by its column's mean. So how can we subtract each column's mean from our original matrix? What conditions do we need for that to work in matrix algebra? So we need the 2 matrices to be the same size. So what we need to do is to get our mean vector, which is length p, to be a matrix of size n by p. That way we can subtract it from the original matrix. And so our new matrix will be a mean matrix where each column just has the mean of that column repeated. So how can we do this using matrix methods? We can post multiply its transposition by L. So we're taking L times the transposition of the mean vector. And so this is what that looks like. So we take, we're going to say XC is centered X, and it equals X minus L times X bar transpose. And so we can see what that looks like for our original X. We subtract our vector of ones times our transpose mean vector. So we have our 4 by 1 vector of ones times our 1 by 3. That's going to give us a 4 by 3, which we can subtract. And so you can see what it does is it just essentially expands our means. So each column is just the mean of that column repeated. And that gives us our centered matrix. And we can, of course, do this in R. So here I'm taking my X matrix, subtracting L times the transposition of X bar, and I get the same result. And the easy way in R is to use the scale function. The scale function is a little bit finicky. By default, it fully standardizes, so it also divides by the standard deviation. We can set scale equals false, and then it won't do that, it will just center. It also attaches these funky attributes onto the new matrix. If we don't want those, we can include this little bracket at the end, and that will just return the centered matrix without the attributes. The attributes just record what the mean and standard deviation were, but having attributes attached to an object can cause issues later if you want to do more operations. So you can practice here. I didn't rewrite the mean vector here, but it was 4 and 5. So if you want to try again, go ahead. If you want to practice getting YC on this matrix, pause here. Then I'll show the answer on the next slide. So here is the mean-centered version of Y. So the next thing we're going to do is something that's possibly half new. So we're going to look at what's called the sums of squares and cross products matrix, which is noted Q in David's notation. I think in the book it's a little bit different. I like calling it Q2. So what this Q, or sums of squares and cross products, or SSCP matrix has is it has the sums of squares for each column of X along its diagonal. So the sums of the squared deviations along its diagonal, and then the sums of the cross products between different columns on the off diagonal. And we use the center data for this because the center data treats everything as a deviation from the mean vector. So every column has a mean of 0. And we get Q by transposing our center data and then multiplying it by the untransposed version. So XC transpose times X. So if XC is what we had before, how do we get Q? Well, we're going to first transpose XC and then multiply it times XC. And we see that gives us this result down here at the bottom. So we see again, what we have here is now a 3 by 4 multiplied by a 4 by 3, and that's going to give us a 3 by 3. So this is a symmetric 3 by 3 matrix, which has the same number of rows and columns as our original X matrix had columns. So you can go ahead and practice this on the Y matrix if you want. First, the results in R for confirmation. So I'm just transposing XC and multiplying it by XC, and you get the same result. So you can go ahead and try that practice on the Y matrix here if you'd like. Again, I'll show you the answer on the next page. I'm not going to go through it same way. So here's the answer, the SSCP or the Q matrix for Y. And Q is a helpful matrix to have. It may not quite be clear yet if you haven't done all this yet, but it's a useful step in obtaining a covariance matrix. So now that we have the sums of squares and cross products matrix, we can define the covariance matrix as 1 over n minus 1 times Q. So essentially, we're just dividing every element of Q by n minus 1. And that should be familiar. This is essentially how we get an unbiased estimate of variances and covariances for a sample drawn from a population. So as a reminder, we have X here, and that's more just to remind you that it's a 4 by 3, so n equals 4. And then we have Q. So to get the covariance matrix of X, we are going to take 1 over 3 times X, because 3 is n minus 1, 4 minus 1 is 3. And that's going to give us our covariance matrix. And so, of course, we can do this with matrix processes by multiplying 1 over 3 times our SSCP, our Q matrix, Or we can also always just use the cov function on x, and you see we get the same result. And so again, you can practice here on the y matrix. So once again, the y matrix is there just as a reminder that it has n equals 3. So you're going to want to take 1 over 3 minus 1 times the q matrix, and that will give you the covariance matrix of y. And so here is the answer in R, just for confirmation. So now that we have our covariance matrix, the last step that we might want to consider here is getting it to be a correlation matrix. And so let's stop and think how we might do this. We probably have a decent idea of how we would do this without matrix algebra. So how can we take what we know and then do it using matrix algebra? So just think for a second, what do we need to do to translate covariance into correlation? So the answer, of course, is we need to go from variance to standard deviation. So we need the standard deviations of each of our variables, and we need to be able to divide by the products of the standard deviations, the pooled standard deviations. So how can we do this in a matrix? Well, what we can do is create a diagonal matrix with only the variances of our data, and we call this D. And then what we can do is we can take the square root of this diagonal matrix, and that gives us this SDs. So d to the 1 over 2 is a diagonal matrix of standard deviations. And then we can take the inverse, and that gives us a diagonal matrix of 1 over the standard deviations. And then we can multiply that by our original matrix, and then again by itself. And that will give us that will allow us to divide by the pooled standard deviations. So one of the reasons this works is when you have a diagonal matrix, you can simply take the square root or the inverse of the diagonal elements. You don't have to worry about all the complicated spectral decomposition and stuff like that. It works out that each element is simply the inverse of the square root. We saw that in the last slide deck. So we have this covariance matrix. So what is the correlation matrix? So what's the first step that we just talked about? The first step is going to be getting the d to the negative 1 over 2. So what we're going to do is we're going to take this diagonal here, and we're going to put it in its own matrix with just a diagonal matrix, so the zeros on the off pieces. And then we're going to take the square root and invert it. So we're going to get 1 over the square root of this diagonal matrix with just that diagonal. And so we see that's here and here. And so we're going to multiply d to the negative 1 over 2 times the original matrix, again times d to the negative 1 over 2. And so we can see what happens if we do this. So first we multiply these first two matrices. So we're going to wind up multiplying 1 over 11 times 1 over square root 11 times 11, 0 times negative 3, 0, 0 times negative 9, 0. So we can see how this is where this is going to go. So here we get the first row after multiplying these first two matrices. So this is only this first part up here. So this first row is now the same matrix over root 11. Then the second row over root 3.67, so on and so forth. And then we still have to multiply it once again by our d to the negative 1/2 matrix. And so we can see if we do that, we wind up with this matrix here where we have 1s along the diagonals. So each diagonal, because here we're going to multiply 11 over root 11 times 1 over root 11. So that's going to give us 11 over 11. And then everything else is going to be zeros because we still have the 0 matrix here, or the zeros on the off diagonals here. So we get our 1s on our diagonals, and then we get our covariances on the off diagonals. So we get each element divided by the pooled standard deviations. And that's going to give us our correlation matrix. So in R, the matrix way to do this is a little bit funky. So we're going to use this diag function to get our d to the negative 1/2 matrix. So the diag function does a couple different things in R. If you apply it to a matrix, it just extracts the diagonal elements, as it doesn't turn them into a matrix. it just takes the elements of the diagonal, but that as a numeric object. But then if you put a numeric object into the diag function, it turns that numeric object into a diagonal matrix. So if we nest the diag inside of diag, this first one is going to get the diagonal elements, and then the second one is going to create a diagonal matrix. So here we see we get the diagonal elements of our covariance matrix and a diagonal matrix. And then we're going to take the inverse of the square root. So we're going to take the square root of diag x, and we're going to take the inverse. In principle, we don't have to use the matrix operations for this again because it's a diagonal matrix with zeros off the diagonal, but it's just convenient to keep doing it just for to be consistent with our matrix functions. So I'm using the matrix square root m and solve, and we see we get our inverse square root diagonal matrix. So this is the standard deviations on the diagonal. And then I'm going to multiply it by the covariance matrix, and then multiply it again by the inverse root diagonal. And you see that gives us our correlation matrix. And of course, we can always check this by just taking the correlation COR function of our original X matrix. And we see that it matches up, we get the same result. So you can practice again on this Y matrix here. So this is the covariance matrix of Y. So how do we get this to be a correlation matrix? You can go ahead and try that on your own. And I'll just show you the result here. This is the correlation matrix.